yes, I'll talk about the subject. In the spirit of this workshop and this trimester, I will review personal work, but I will also mention ongoing work and open problems. So the outline will be, well, in the first two parts I will motivate this subject, then I will discuss subtleties of stochastic inflation related to Ito and Stojanovich interpretations, discuss multifield setups, and so on, if I have time. So, well, there's been a nice introduction to all the subjects by Vincent Venin yesterday, which will help me to skip some details. But basically, well, we all know that well, we have cosmological inflation, which does a very nice job at least phenomenologically explain all the data. This marvelous Planck data. That's not the very last papers, actually. And according to this paradigm, you know that the quantum the fluctuations we see in the sky of the CMB and of the large-scale structure are supposed to be quantum fluctuation stressed to cosmological scales. So really, at the core level, you have to mix quantum field theory and general relativity in some sense. And however, in the conventional formulation of inflation and of cosmological perturbation theory, this is not that obvious. As you know well, what we do usually, at least, is we split fields, both the fields active during inflation, the space-time geometry, as a background, which obey fixed classical equation of motion, and superimpose fluctuations on top of that. That we treat in a quantum mechanical way. So, of course, we don't have a full theory of quantum gravity, so that's a nice first step. That's not conceptually not very satisfactory. It's also, and more importantly, it breaks down. It's expected to break down for very light scalar fields. Basically, because if you have the limiting case of a constant potential, you have no classical motion. So, well, you are dominated by the quantum diffusion and not by the classical motion. And as we heard about yesterday, the stochastic formalism aims at addressing these conceptual issues. So, a brief summary of what all this is about. Well, you know what happens during inflation. If you have time, you look at physical scale. So physical scale gets stretched by the expansion of the universe for a fixed co-moving scale k, and any scale k during inflation crosses the Hubble radius at some time, right? And this Hubble radius physical Hubble radius is almost constant. And the idea of the stochastic inflation formalism is basically to replace the background, the fixed background, the k goes to zero formal limit by the sum of the super Hubble modes with some margin. So those are called infrared modes. And because at any instant of time, you have UV modes which become infrared, you have modes which cross the Hubble radius, you have a continuous flow of UV modes joining your super Hubble sector. So you have basically an open quantum system. And the idea that Straubinski put forward a long time ago is to try to derive a classical effective theory, but stochastic, for the coarse-grained fields. So for not the background, but for the super Hubble part of modes. And well, you can arrive under some assumptions at this type of equation, which is basically the Schroer type of equation that you would expect for the background. Time dependence of phi with respect to the number of ethyls is related to the slope of the potential, plus some random kicks, which well, are physically motivated by the fact that at any instant of time you have modes with fluctuations of order h divided by 2 pi for light modes, which join the infrared sector. So stochastic inflation, the stochastic formalism in general, has lots of success. Well, it has been shown in a series of papers that it reproduced really non-trivial results from quantum field theory in curved space-time. So that the series of famous work by Straubinski and Woodard and so on. You take the famous lambda phi to the 4th theory. You just use this very simple equation, which is incredibly simple to solve. You deduce renormalized 2-point function, 4-point function for the lambda phi 4 theory, and that matches horribly complicated result from renormalized quantum field theory in curved space-time. And without, somehow explain why the success of this. Another recent success is the fact that Straubinski and Vincent Renaux showed how you can recover conventional perturbation theory in a suitable classical limit, right? You have something quite general, and just the usual description emerges as a particular limit. However, there are open questions that I will mention in the talk. This is an effective field theory, so it has its own regime of validity, it has limitations, and they are not always they are not always delineated. Some I will mention, and that has already been discussed in the literature, are the fact that, well, in general, the noise can be non-Gaussian, although it's supposed to be suppressed by the small interactions. It's also in general non-white. Something that is not often acknowledged is the fact that actually the system is non-Markovian. I will come back to that. This was just on slow roll. You may like to extend this to phase space analysis. And something that I will talk about is curved field space and the issue of covariance. And that's something that is relatively new, I think, to my knowledge in this field. And why you want, in which kind of subject you may want to study these kind of things. Well, of course, the whole idea of eternal inflation in the multiverse is based on these kind of things, although its regime of validity usually is not there. We've heard yesterday in Vincent Renaux's talk that, well, you have to use a stochastic formalism in some sense to study primordial black hole production, basically because you need for this very flat potentials in which is quantum diffusion are important. And another subject which motivates this is the called geometrical destabilization of inflation. That's some phenomenon that I have introduced a few years ago. So let me present it to you and do a few minutes of propaganda about this idea. It's a very simple idea, which I think it has rather important implications for inflation. Well, we know that first realistic inflationary models have multiple fields. Bottom up or effective field theory point of view, you know that you have other scalar fields than just one inflaton. That's not reality. You have to take them into account, maybe to derive an effective field theory which is single field, but you have multiple fields. And many people, of course, in the past years studied how this can impact things. And these fields, importantly, live also in an internal space with curved geometry. By this I mean that they are non-linear sigma models. You have derivative interactions. And we know the physical effect of curvature. That's very easy. If you take neighboring geodesics, if there is no curvature, they will stay parallel. If the curvature is positive, they will get closer to each other, and if the curvature is negative, they will diverge. And this very general fact about curvature applies as well for inflation. And what I think is interesting is that it can easily overcome the effect of the potential and destabilize what you may think can be stable inflationary trajectories. So really, it's quite general, but just the basic idea. Take what can be the simplest hope of realistic models in model building. Take just two scalar fields, take a potential. Imagine you solve the eta problem. We know it's not done. Imagine you have a light scalar field. Imagine you did all what is possible to stabilize the extra scalar field by giving them a large mass. So we end up with this usual story of inflation arising in a valley with steep walls that will explain why we observe single field inflation, although in the true theory there was multiple scalar field. And this was the potential. As I tried to motivate, actually you have not only the information in the theory, you have the curved field space. And this can lead to geometrical instabilities. It's really like, if you want an analogy, you play with a charged particle which is confined on a surface. If you have an electric field which confines it on a potential well, that's nice. But if the surface itself is bumpy, there will be a competition between the two things, and the geometrical part might win. Technically, that's just the geodesic deviation equation. You can see that the relevant mass squared of neighboring geodesics has a contribution which is proportional to the curvature in a way which makes geodesics diverge in the presence of negative curvature. So I don't go into much details, but I think that's really something that has been overlooked and that's very important. That's really like the eta problem. The problem is basically you want your scalar field to be light and you have some high energy corrections which spoil your flatness of your potential. Here you would like all the other degrees of freedom, not the inflaton, to be heavy, and you have high energy corrections which can spoil that and, for example, making them tachyonic. But there is no symmetry, I think, to help in this thing. No, there is no equivalent of the shift symmetry, so I think that's an important problem. So I could give an entire talk about this subject, but let me just look at a very simple toy model where you can have this kind of things. That's a really simple one. You take what you think is your inflaton phi with your potential that you like and love. You take another scalar field with a mass which is with a heavy mass much greater than h. You think that things are stabilized, but you just add derivative interaction suppressed by a high energy scale. And in that case, it's obvious you don't need to do differential geometry, that the effective mass along chi equals 0 felt by chi is this potential contribution mh squared, but there is also a contribution here coming from the fact that, well, phi dot is non-zero. And phi dot is related to epsilon. So although epsilon is small during inflation, you have this contribution. And what matters is that what physically appears, if you look at the dimensionless masses, m squared divided by h squared, this thing can be very large, okay? But this one is negative because it's a negatively curved field space. And even a modest hierarchy between the curvature scale m and the Planck mass can boost this, although epsilon. So naively you can think it's slower suppressed by epsilon, but with reasonable numbers, well, back in the past that may be negligible, but epsilon typically grows during inflation and can overcome and this can overcome the epsilon suppression. So it's a bit like hybrid inflation. You evolve in a potential which is stabilized, and then you have a tachyonic instability because when this quantity grows and reaches 0, your field chi is massless, and then it becomes tachyonic. And well, you can wonder where the system would like to go. Well, we studied recently. Well, there is a nice, if you want, attractor trajectory somewhere else in field space where you have a combined effect of the potential, which tends to stabilize you in that way, and the geometry gives the effect that you don't want to be here. And so clearly there is a kind of a gelaton type model here where the two things. But the thing is, I don't know at least, whether we reach this phase. And because for this, you have to take into account the back reaction of fluctuations on the effective background. So imagine you are here, you have some small fluctuations of chi, because the field are stable, and then you reach this critical point where this mass is 0 and then negative, and so you have basically a spontaneous symmetry breaking. You have some patches of the universe in which you have fluctuations of order h and of order minus h. They all grow, and you would like to know whether this back reacts and whether this ends inflation.
Sorry.
Yes?
Is this sort of non-standard kinetic term?
This is what?
Necessary for instabilities.
If the kinetic terms are standard, indeed there is no geometrical instability. The geometrical instability comes from the fact that, in general, indeed you have nonlinear sigma models. Whether they are God-given in supersymmetry with your Keller potential or in an effective field theory point of view, you have such type of corrections, which, by the way, do not break any even approximate shift symmetry of the inflaton. Okay, and I think this is important to understand what is the fate of the instability, because the consequences can be very different. If the homogeneities grow so much that inflation ends prematurely, so much before what you would think if you don't see this instability, this has lots of consequences. You can derive some rather universal bound on curvature scale, which can be interesting for string theorists. Of course, if on the same potential you end up much earlier, 10 or 100 or 1000 EFOLs before the standard end, this modifies completely the way you interpret even the current data in terms of ranking models. So we've done this analysis with Christophe Turzinski and Vincent Renaux. Well, if the homogeneities are shut off, if the instability is only transient, well, probably you will reach this attractor, which we call sidetrack, right? Because you're off track along the potential. And it has a reach phenomenology. We studied that recently with Sebastien Renaux-Petel, a postdoc here at IAP, and John Ronine. And so there is a rich phenology. I encourage you to read these papers. There is a nice corner of theory space, if you, relatively unexplored, corresponding to a single field effective theory with imaginary speed of sound. That is interesting. So all this to motivate the fact that we like to understand, well, back reaction of fluctuations, whisker field space, and so stochastic formalism in general situations. So after this long introduction and motivations, and let me discuss in a bit more details stochastic inflation and subtleties. So we'll begin with single field to set up notations and clarify things. And because this is supposed to be, well, this is EHP, and this is to be a workshop about the mass of cosmology. Let me remind you, or let me show you some basic things about stochastic calculus, which you may not have encountered. So, as physicists, we're used to play with, well, we used to see this type of so-called Langevin equations. I take one variable x, which is a random variable. It evolves as a function of time n, which would be the number of e-folds in our case. It has a deterministic drift, and it has another part with a Gaussian white noise. Okay, and well, you can see that as a continuous limit, and you should see that, it's not mathematically defined otherwise, as a continuous limit of some discrete processes. All right, you have some different times intervals. You want to know how you go from your value x at time ni to the value at time ni plus 1. And well, if this was just a standard differential equation, you would just take h times delta n, but you have this part. And basically that's called a Wiener process. At any instant of time, you multiply this function g not by delta n, the usual time spread, by something which is drawn from a Gaussian distribution and which is typically of order square root of delta n. That's basically what this means. But the important thing is that usually we don't really care about the discretization, in particular how to go from point ni to point ni plus 1, we don't really care, and we just take a point in the middle, or I mean in this interval. But actually, where this is true, whereas the general properties of x in the continuum limit does not depend on this precise choice for standard differential equations, they do depend for stochastic differential equations. And there are several choices of discretizations, alpha discretizations. I will concentrate on the two more well-known ones, more physical ones, so-called Ito and Stratonovich. That may ring a bell for about your statistical physics course. The idea is, so if you want a natural choice, a simple choice would be the Ito, which is, okay, the idea is you are at this point and you want to know, okay, what is the side of the jump, and you just evaluate the function, which depends on x, at the value it had just before. Okay, it has the merit of simplicity. Another way is called the Stratonovich, or the midpoint rule, where you evaluate, where you take the average between the points. So it looks like, let's say, if you want to study differential equations, this looks like an implicit method. You are looking for the function at time i plus 1, and you're using a midpoint. And both have, let's say, pros and cons. Well, this is simple. However, if you take your stochastic variable x and you build another function made of it, like x squared, so any function f of x, the standard chain rule, the standard change of variable doesn't work. And the function f of x is not just this, but has this new part. And that basically, physically, you can see that the fact that this counts like dn, and this counts like square root of dn, so you have to take the square of this. If you take into account this seemingly more complicated choice, however, you respect the standard chain rule. Okay, but physically, you want something physical is basically the PDF of your variable. So you can derive in all these setups a Fokker-Planck equation for the probability distribution function of observing your stochastic variable x at time n. And it obeys, therefore, so Fokker-Planck equation, which gives you the time derivative of the PDF as a Fokker-Planck derivative operator acting on P. And so there is a part which corresponds to the drift, somehow the classical part, and a part corresponding to the diffusion. G is the amplitude of the noise term. However, whereas the drift in Ito is simply the classical drift, the one that was appearing in this, as a classical part in this equation, in Stratonovich, you have a so-called noise-induced drift. So you have a new contribution to the drift coming from the derivative of the function g. So basically, in the two other ways, you have related problems. You have either you follow the standard chain rule, but you have a new term here, or you don't, and you have a simple result here. Okay, and so once you are given a stochastic differential equation, you have to know physical consequences will depend on whether you interpret it in Ito or Stratonovich. And if you look at the literature, there are different answers. Many papers say we have to use Ito to respect causality. That's not a good reason, actually. There are many fields which of physics in which people use the Stratonovich interpretation. It's just a midpoint. That's an implicit discretization, but there is no acausality in that. Stratonovich, actually, choice in our field has been, as far as I've seen, motivated only in one paper, right? Straubinski a long time ago, proceeding, but physically it's used in lots of other fields in physics. It physically corresponds to the fact that white noises, so okay, the correlation function being a delta, is just a convenient mathematical idealization of some processes with a finite time scale. And so typically the physical motivation would be if you have a smooth splitting between the UV modes that you don't care about and the infrared modes for which you derive the effective field theory, it would typically motivate Stratonovich interpretation. Straubinski in particular often explains, mentions that this subtlety exceeds the accuracy of the stochastic formalism. And we revisited a bit this question with a new perspective of the covariance. So let me take a single field in slow roll, and let me take this equation as our starting point. Of course, if there is a conceptual difference between test and non-test scalar fields, if you have a test scalar field, h is fixed, the theta or even time dependent, but it's a well-known deterministic function, then you have no ambiguity in Ito or Stratonovich. If your field phi is driving inflation, well, h is a function of phi, so you have this multiplicative noise and this Ito or Stratonovich ambiguity. However, I will show that in this case there is basically no difference. So I can rely on Vincent Venant's nice talk yesterday. There is a well-known now stochastic delta in formalism which enable you to predict properties of the curvature perturbation with this type of things. The number of e-folds starting from a given point becomes a stochastic variable from which you can deduce zeta, the curvature perturbation, being just the fluctuations in this number of e-folds. So as I explained the other day, if all this information is in the number of e-folds, the stochastic variable, the number of e-folds as a function of phi, equivalently, all the information is in basically its Fourier transform, the characteristic function. The details are not important. You can derive basically from the Fokker-Planck equation, you can derive a kind of Fokker-Planck type equation for this characteristic function. The only thing that matters is what is the difference between Ito or Stratonovich. And if you introduce V, which is a dimensionless potential in Planck units, you see that you just have a correction factor which is 1 minus something like V. And V has to be much less than 1 to be in the classical regime, in the sense that you are not dealing with quantum gravity. Okay. V is much less than the Planck mass to the 4. So in that case, this condensed formalism show you that there will be no practical difference between Ito or Stratonovich in whatever regimes. This can be highly stochastic or classical, but there will be no difference. And indeed, you can solve things numerically. That's similar to Vincent Venant's slide yesterday. You take a given model, and when phi is very small, you have a very flat potential. You expect quantum effects to be large. And okay, I don't go into details, but basically in this region, the potential is so flat that quantum effects are important. And indeed, the stochastic results are very different from the classical one, However, Ito or Stratonovich would give the same result. So if you want, you have a theoretical errors which is completely under control. Okay. Now let's go to multiple field. So now that you hopefully get to know the notation and the concept of Ito and Stratonovich, it's very easy to extend that to several variables. So with the idea of applying that to several fields, you just have several XA. You have again drift, and now you have a sum. So each component receives multiple kicks from independent Gaussian white noises, right? Because there is a summation over alpha here. And exactly in the same way, you can derive a Fokker-Planck equation, which gives you the time derivative of your PDF as a derivative operator acting on your PDF. And there will be a drift, and there will be a diffusion. The drift now is now a vector. There will be a diffusion matrix now. The diffusion matrix is typically it's like the square of these things here. So there is again a summation, implicit summation over the different noises alpha here. But the drift differ in Ito or in Stratonovich with again a noise-induced drift when G depends on X, which is the case for non-test scalar fields. So I'll come back to how we can hopefully one day derive this with some degree of rigor, but let me first try to see what would be reasonable Langevin equations for a multifield generalization with a curved field space. Typically, you can expect something like, the background equation of motion and slow roll plus some noise. And what would be the noise? Well, you would know their correlations. And the standard result of basically nonlinear sigma models and correlations of UV modes is that the correlation is white noise, and the amplitude, the famous amplitude h divided by 2 pi times Gij. But this is not yet a stochastic differential equation. That's an important point. It's really, if you don't want ambiguity, you have to write this as a sum of some functions times some independent Gaussian white noise. And here I just wrote this as a block, and I only know their correlation function. So to write this as a stochastic differential equation, you have to write something like the psi are some functions times independent noises. And you can easily do that with introducing field binds for your metric, with any set of field binds. This will, this and that if you want, will verify these physical property of the noise that you can expect. But the field binds are arbitrary. You can make any local change of field binds. However, this will change things, because if you remember, it has no impact on the Ito Fokker-Planck equation. The Ito Fokker-Planck equation, even the diffusion matrix, depends somehow just on the square of this. So in that case, on the true correlation matrix of the noises, and that's it. Whereas in Stratonovich, the derivative of this, in that case, arises. So the derivative of the field bind. So you would have different result in Stratonovich depending on the choice of field binds, which is arbitrary. So that looks weird. So Ito seems to be a preferred choice in that case. However, the thing is that field space covariance is only respected with the Stratonovich interpretation. And you can see that as a consequence of what I show you, which is that the standard chain rule is only valid in the Stratonovich interpretation. Otherwise, you have to use the Ito lemma. So it's problematic. Just to see what this means in practice, when you discuss about covariance, it's of course simpler to use a scalar. So in terms of the PDF P, you take a rescale PDF by the determinant of the metric, and this should be a proper scalar under field definitions. Any sensible stochastic theory should be manifestly covariant in terms of this scalar object. And in Ito, it will not be. In Stratonovich, if you derive the equations using the formula I showed you, you will find something which is manifestly covariant. The time derivative of this scalar object is given by this formula, and everything here is covariant. You have covariant derivative in field space. This is a covariant derivative of the potential, and so on and so forth. However, you have this second line where you have a dependence, a spurious dependence on the arbitrary choice of field binds that you had to introduce by hand. So, and this arises in curved or flat field space, right? Because I motivated things by curved field space, but you can play with just a d phi squared plus d chi squared flat field space model. You might want to use polar coordinates, and the result should not depend on that. And you can change arbitrarily the field binds. So you have this conceptual issue. By the way, so this shed also a new light on single field inflation. I said in single field inflation, you don't really care, it's in the theoretical error. But even for single field inflation, at the expense of having non-standard kinetic term, you can relate, when you talk about a single scalar field, usually we take standard kinetic term, but we can refine phi to phi tilde, you will have non-standard kinetic term for this single scalar field. And in that case, there would be no ambiguity. So here the ambiguity comes from the fact that you can choose field binds as you want. But if there is, okay, in a 1D manifold, whatever system coordinates you use, there is just one direction, or one or the other one, for the field bind. And okay, of course, this arises quadratically. So if you allow field redefinition in single field through roll, that shows you that Strotonovich is the only interpretation. Therefore, and in that case, the result will be unambiguous. Yes?
Can you say again why the formalism?
So I don't give the result, which would be non-manifestly covariant and complicated for Ito, but the reason is that the standard chain rule does not apply, if you want, that these terms in the equation, the drift, do not transform as vectors in the Ito thing, whereas this thing, you would like it to be a vector in field space. Okay, for the moment, I just postulated this equation, so you might want to have an idea of how you can derive that. That's complicated. Okay. The general logic is, again, you split your fields into an infrared plus UV parts. And, well, we try to derive general things for nonlinear sigma models in full phase space. You can take a heuristic approach, which is just take the equation of motion, put these ansatz into this, and take into account the time dependence of the coarse graining scale, the fact that basically UV modes become infrared, and you end up with some equations. You can do something more rigorous, which is more complicated, which is really integrating out UV modes as a result of the action. There is a bit of technology. You have to use the Schwinger-Keldysh formalism because your background is time, because things are time dependent. The effective Hamiltonian action, if you keep the UV modes Gaussian, it's easy to integrate out. Maybe I skip. How much time do I have left? Okay. So I will not concentrate on that, but you can, if you do that, derive Langevin type equations in phase space. Okay, you have something which looks like the previous equation, but now phi dot does not depend on the derivative of the potential, but on its pi, which is momenta, and you have the derivative of the momenta in terms of pi, phi, and some noises. And well, you have some nice covariant derivatives. The Hamiltonian constraints now gives you h as a function of both all the phis and all the pi. But this is not at all yet stochastic differential equations and easy things. In particular, here I didn't give details about what are these things, the noises. What you can predict is the correlation matrix of the noises. Basically, they're given by the power spectra of your UV modes or their momenta in your given infrared background. But the given infrared background has been influenced by all the past kicks of the noises. So what I mean is that, strictly speaking, things are non-Markovian. And when we write that the amplitude of modes is h divided by 2 pi, that's a reasonable approximation, but we might want in the future to understand under which conditions memory effects and non-Markovian behavior can be neglected. Okay, if you don't integrate just the Gaussian part of the UV modes, it will be non-Gaussian. You can typically expect that it will be non-negligible. I guess that's not that complicated because it will not, to deal with, and in terms of principle, it will not be a Fokker-Planck equation, but a so-called Kramer-Moyal expansion, but it can be under control. The fact that physically the splitting between the UV and infrared modes should be smooth introduce non-white noises, and that's more complicated. However, what I want to stress is that, okay, these are interesting things, I think, for future research, to delineate the range of approximations of the usual thing that we do, Gaussian, white noise, Markovian. But even if you believe in that, simplify the problem, there will be again the issue of covariance. I'll be brief, but basically the same ambiguities arise. now you are in the full phase space. If you are using proper field phi and pi with some indices down, that's a proper scalar in phase space. But in the same way, you need to introduce some arbitrary square roots of your correlation matrix. It's just more indices, more complicated. But in the same way, the Ito formalism will not depend on this, but will not be covariant. The Stochanovich will be covariant, but at the expense of this kind of frame dependencies. Just to give you an idea of what this looks like, this is a nice covariant Fokker-Planck equation in phase space. You have some derivative operator here, which are phase space covariant derivative operator. But you have this second line, and this second line is put formally here. It's some derivative operator acting on G, acting on derivative operator acting on G times P, and G are these square roots. And bottom line is, well, this will depend on your arbitrary choice of how you represent the noise. Just one nice thing that I like is that even if you forget about the subtlety, which are the core of this thing, this equation can be useful on its own. It's just a neat reformulation of the deterministic evolution in nonlinear models of inflation in a Boltzmann-like type. So that can be useful. Of course, you can just solve your differential equation, but if you want to study initial conditions, sensitivity to initial conditions, and things like that, I think that can be useful. And you have, what, 5 minutes? Something like that? Okay. Okay, I've explained you, let's say, problems, the fact that everything is complicated, but okay, and we have to have some degree of approximation to try to write down something, and I think for the future, we need more work to delineate things. Here, basically, I'm showing practical consequences if I'm assuming something. I'm assuming that this stochastic anomaly, call it like that, but you have a classical symmetry at the level of your action. You can do any field redefinition you want. Classically, it's okay, and now it's broken by taking into account stochastic effects. So it's really an inflationary stochastic anomaly. I'm assuming that this is an artifact, that a proper treatment in quantum field theory would solve this. This technically would be like adding a suitable noise-induced drift. I'll just show you again this equation, for example, in phase space. You see that this thing that we don't like, it has the same structure as a drift. It is something with an index I times the PDF. And so if you started initially from not the slow roll equation for the drift, but with a correction which knows about the noise, this would disappear. So basically, because I don't know right now how to do better, I skip that. And I postulate that this, for simplicity for test fields in the zeta space, is a reasonable covariant equation for the diffusion of light scalar fields in curved field space, and so in the overdamped limit, so in the slow roll limit. And well, this is just actually the simplest covariantization to multifield of the usual equation. Of course, as soon as you do covariantization, you can wonder, okay, can I have added a Riemann term somewhere because this is equally covariantization? And I think in that case, the physical answer should be no, because we know the microphysics. We know what the curvature is doing. The curvature is appearing in the effective mass matrix of the fluctuations. That's what's appearing in this geometrical destabilization of inflation that I was mentioning. So if I concentrate on effectively light scalar fields, basically this should not intervene, although this should be in general. And from this, it's completely easy to derive results. So let me finish quickly. Just take a two-field model, a field space geometry of that type, which has been quite studied. In that case, it's super easy to derive evolution equations, let's say, for the moments of phi to the n. And you see that everything here depends on phi, except the potential. So for some separable potentials, v of derivative of the potential depends only on phi, and you can solve this iteratively for any, let's say, polynomial dependence at least on v and b. And so we just applied this to a very simple model, which I think is interesting. You just take the famous lambda phi to the 4 model, and you embed that in the hyperbolic geometry. So that corresponds just to take, okay, v of phi being that, and b being this. That corresponds to a hyperbolic plane with this curvature. Of course, there is no unique way of embedding, lambda phi 4 in the hyperbolic geometry. That depends on the precise choice and interplay between your potential and your metric. That's it. In that case, the Z2 symmetry that you usually have is broken by this. And it's straightforward to deduce at any order that would correspond to loops in the quantum field theory your function. Let me concentrate maybe on phi 2. So in the usual phi to the 4 theory, this is 0. And you know phi 2, it initially grows, it initially grows like n, that's the famous secular growth, just because you have a random walk. And then you have corrections at over lambda n squared and lambda squared n4. So you have an expansion in lambda n squared. Here you have an interplay and you have both this and, if you want, corrections, again, by a small coupling constant, which is a ratio between h, the energy scale of inflation, and this curvature scale, times n. And so it's very easy to derive, but just like it was useful to compare for lambda phi to the 4 the stochastic result to the quantum field theory computation, I think this would be interesting, but complicated, to try to do the quantum field theory computation of this type of model and try to check if the coefficient matches and so on. This has been done for lambda phi to the 4 in the single field case, and the fact that they agree is quite a success of the stochastic formalism, because this is super easy to derive, whereas it's horribly complicated in the quantum field theory. Just one thing is, well, as usual, when you wait long enough, when n overcomes just even the small coupling constant, any perturbative scheme is irrelevant. So you would like to resum this and to know the late time behavior. That's what the stochastic formalism does for you. And it's easy, in that case, to do it. If you look at this equation, for any actually potential v or b, you see that you have the same b, the non-canonical function in the metric, appears in exactly the same way as the potential. So actually, although it's a two-field model, you can predict all the statistical properties of phi as if it was a single-field model with a modified effective potential, which depends on the potential and on the term appearing in the field space metric. In that case, it's easy to use standard results and, for example, to predict what is the equilibrium distribution when it exists, and so on and so forth. So let me conclude, well, concrete things that we've done and then open questions. So basically we highlighted this Ito-Satanovich dilemma and its relationship with covariance. That's something that I discovered afterwards, which is well known in statistical physics, and well, they have the same debates. There is no well-defined answer unless you know the microphysics of your problem. In single fields for a wall, okay, this disappears in Satanovich at least, but as soon as you have multiple fields or even a single field but in a full phase space, you have this ambiguity to take into account. And okay, we look at concrete models with a postulated, if you want, Fokker-Planck covariant equation. And so last slide are open questions, which I think are interesting for the future. So I'm particularly interested in this geometrical destabilization and what is the fate of the instability and what are the general consequences of this for inflation. So I remind you that similarity with the eta problem, but the fact that there is no symmetry to protect, to solve the problem, I think is sufficient to show you that it's very important. And okay, something I've already stressed, it's important to scrutinize the foundation of stochastic inflation. There are many things to me approximation, especially to understand. The non-Markovian one, I think, is very important. And last thing, this inflationary stochastic anomaly, as we call them, seems to be quite well the stochastic counterparts of something which is well known and difficult in quantum field theory, which is maintaining general covariance. And so I think there are many things to do relating this quantum field theory treatments, cosmology, and statistical physics along this line of sight. So I thank you.